Good evening, everyone, and welcome. My name's Matthew Scott. I'm president of the Carnegie Institution for Science. I'll be introducing our speakers in a few minutes, but first, this evening was co-sponsored by the Embassy of the Philippines, and we're very honored to have Ambassador Cuija here with us tonight, and he'll say a few words to start the evening. So thank you and welcome.
Dr. Matthew Scott, President, Carnegie's Institution for Science, Judge David Tattel and Dr. Edith Tattel, convening leaders of Carnegie's new Handling Hazards program, Dr. Chris Newhall, USGS volcanologist, Dr. Renato Solidum, Director, Philippine Institute of Volcanology and Seismology, friends from the Smithsonian Institution and the US Geological Survey, Ambassador Tom Hubbard, and other esteemed guests. Ladies and gentlemen, good evening to all of you. On June 12, 1991, or 25 years ago yesterday, while the Philippines was celebrating its Independence Day, Mount Pinatubo, after a 500-year-old slumber, spewed a huge cloud of volcanic ash and gas. 3 days later, the second largest volcanic eruption of the 20th century, and by far the largest eruption to affect a densely populated area, occurred. According to various sources, the volcano's cataclysmic eruption resulted in the death of more than 800 people due to collapsed roofs, from mud flows known as lahars, and from diseases in the evacuation centers. 650,000 workers lost their jobs. 1.2 million people lost their homes. 58,000 people had to be evacuated from within a 30-kilometer radius of the volcano. The cost of damages was estimated at about $700 million. 2 U.S. military bases in the Philippines, Clark Air Base and Subic Naval Station, were also heavily damaged by ash from the volcanic eruption. Moreover, the environmental effect of Mount Pinatubo's eruption was felt worldwide. Thankfully, prior to the eruption, the collaboration between PhilVox and USGS resulted in intensive studies of the volcano's past eruption history, timely forecasts and accurate predictions, thus prompting the evacuation of 75,000 people living in the lowlands around Mount Pinatubo, and of the 15,000 American servicemen and their dependents from Clark Air Base before the June 15 eruption. Hundreds of lives were saved, and property was protected from destruction, including aircraft and other equipment that were flown to safe areas or covered. How did the Philippines cope with the aftermath of Pinatubo's eruption? Undaunted by the magnitude and extent of the destruction brought about by the eruption, the Philippine government adopted teamwork, or kabisig, and vigorously pursued rehabilitation and reconstruction programs. The government emphasized the importance of cooperation and coordination among national and local government agencies, the private sector, NGOs, and the survivors themselves to prevent duplication of efforts. Development strategies included resettlement of highlanders and lowlanders, livelihood programs focused on agriculture, and industry providing quick generating income opportunities, delivery of basic social services, and infrastructure rehabilitation and reconstruction. Moreover, with the assistance of foreign governments and international funding institutions, the Philippine government was able to pursue its recovery and rehabilitation plan more efficiently and effectively. With the accomplishment of urgent development projects, the affected communities were able to quickly recover from the disasters, and the government was able to institute necessary disaster mitigation measures. Ladies and gentlemen, Mount Pinatubo's eruption does not evoke good memories for Filipinos, especially for those who live in the heavily affected areas of central Luzon. It brings back images of the Lahar flows, people killed, 364 communities, and 2.1 million people impacted, 2,000 homes completely destroyed, pyroclastic flows with hot volcanic rocks killing vegetation and rendering land infertile. So why is there a need today to remember the natural catastrophe that happened thousands of miles away from the United States? Because like what happened prior to the eruption of Mount Pinatubo, the need to collaborate in studying natural hazards and information sharing will reduce disaster risks. The lessons from the Mount Pinatubo eruption remain relevant because future eruptions like that which was experienced 25 years ago would come from volcanoes near large populations. Tonight's public lecture and Carnegie's Handling New Hazards programs are therefore much needed and important. Many of you may be wondering, how is Mount Pinatubo today? 25 years later, local communities have rebuilt their lives from the very lahar that took away what they had. Lahar is quarried and sold as construction material or turned into handicrafts or souvenirs. I invite you to please visit the Philippine Embassy's booth at the lobby to see the sample products derived from Mount Pinatubo's ashes. I'm also happy to share that Mount Pinatubo is now a popular ecotourism destination. Some locals of the affected areas, including the indigenous groups or ETAs, have been trained as tour guides. Climbing up Mount Pinatubo has become an adventure trip of a lifetime, and there are many ways to get to the top. Hiking or driving up the valley. Visitors also go to see the caldera with a crystal clear water pool in the crater of the volcano. Visitors used to kayak and swim there until the imposition of restrictions on these activities. Mount Pinatubo is about 3 hours away from Manila. Almost 3,000 climbers trek to Mount Pinatubo every year between November and May. Once again, Filipinos have proven the indomitable spirit of humanity and demonstrated their resilience. Before I conclude, let me share that the word Pinatubo means made grown in Filipino, national language of the Philippines. I would like to thank Dr. Newhall and Dr. Solidum for your joint efforts to make our knowledge grow. I express the hope that when we go out of the doors of CIS tonight, we will have a better understanding of our environment and will be more prepared when confronted with natural hazards and similar disasters in the future. I wish you all a wonderful evening. Thank you.
Thank you very much. I really appreciate the Embassy's support for this program. So now to introduce our talks. On the afternoon, I think I can go ahead here. Let's see, okay. There's a location for you. On the afternoon of November 13th, 1985, the 5,321-meter volcano Nevado del Ruiz in Colombia, South America, erupted, and it sent slurries of pyroclastic material, mud, and water down its flanks at an average speed of 37 miles an hour. Seismometers in the region at that time were of limited quality, and the signals they showed that warned of the volcano's impending activity, present and impending activity, were not fully understood. An American expert had told the press and public that the volcano could not hurt populated regions beyond 6 miles away. The director of the Geophysical Institute at the Jesuit University in Bogota had written in September that, quote, "Today, because of our monitoring, we can tell the entire population that nothing is happening on the volcano that threatens the inhabitants of the region. If and when it is necessary to declare an emergency, the Geophysical Institute will do it." before would only alarm the population without reason, unquote. These messages reassured local chambers of commerce who had been irritated by alarmist messages from some scientists, calling them volcanic terrorism. Thick clouds concealed the eruption initially. At 9:30 that night, about 6 hours after the main eruption, huge mud flows emerged from the clouds. High on the mountain, heat had melted millions of tons of glacial ice. The flows descended into all 6 of the mountain's valleys, where they grew to nearly 4 times their original volume. At 10:30 p.m., let's go ahead here. At 10:30 p.m., the mud reached a village 15 miles from the mountain and buried about 1,000 people in about a minute. At about 11 p.m., debris flows roaring down in the night. The town of Armero was completely destroyed, and over 23,000 people died. It was the 4th deadliest volcanic eruption in recorded history and the 2nd deadliest eruption in the 20th century. Mount Pelée in 1902 caused even more loss of human life. It was the first time in 140 years that Nevado del Ruiz had erupted so violently. The mountain had sent deadly flows down in the years 1595 and 1845. The residents had understandably become complacent, calling the volcano a sleeping lion. Although scientists had been monitoring the volcano for years and were aware that it was in an active state, even distributing hazard maps just a month before this eruption, local authorities were not inclined to listen. Warnings to the town of Armero during the quake were too late, since no one knew whether to trust them or how to respond to them. Even the Colombian Congress accused the scientists of scaremongering. Consequently, there was little warning and no evacuation, even in a situation where an evacuation would have been very effective. The disaster at Nevado del Ruiz was a sobering lesson. In response, just a year later, the volcanological community implemented a volcano disaster assistance program jointly funded by the US Geological Survey and the Agency for International Development. The program provides rapid response mobile volcanic monitoring equipment to assist scientists in foreign countries facing a volcano crisis or potential crisis. Partly as a result, in 1991, just 6 years after the eruption I've just described, the eruption of Philippines' Mount Pinatubo, though much more severe than the one at Nevado del Ruiz and occurring in a much more populated area, resulted in only a few hundred deaths and the saving of millions of dollars in prevented property losses. According to the US Geological Survey, the savings in property alone were many times the total cost of the forecasting and evacuations. The success at Pinatubo illustrates vividly the importance of volcanic monitoring and the importance of communication and response. And as you've already heard alluded to, we have here today and tomorrow a superstar group of experts on volcanoes, hurricanes, and earthquakes discussing principles of both the science and new science and science policy that should be derived from intelligent application of that science, the issues of communication and social policy and government policies that are important in this context, and the ethics of scientists properly informing the public without inducing either undue alarm or undue complacency. And these are very difficult and complex issues, and we had a fantastic day today hearing from this team of experts who's assembled with us, and I'm very grateful to them for coming. It's the first in a series of science and society programs we're forming, and this group will be producing public events in the future based on the work they started today. We don't know exactly what form those will take yet, but you will be hearing about them if you're on our mailing list. Okay, so back to Pinatubo. Unfortunately, despite the vast amount of historical knowledge that scientists have accumulated about active volcanoes, and despite all the tools now in use to predict eruptions, tools that measure seismic activity, changes in gases, movement of magma, predicting exactly when a major volcano will blow remains an inexact science, and convincing the public of danger amid that uncertainty remains a challenging responsibility. The stakes, however, have never been higher. Some scientists estimate that nearly 10% of the world's population lives in or near volcano hazard zones. As well, airplanes pass over hundreds of active volcanoes every day, and eruptions have caused millions of dollars in airplane damage and in prevented travel. To help scientists better understand the relationship of prediction to mitigation and public action, the Carnegie Institution is sponsoring this working group that we've had here today. And it's looking at best practices to the extent there are best practices, and looking at alternative ways of approaching the problem, especially a way of conveying hazards to the public in a way that is balanced. Among the members of this committee are two eminent volcanologists who were on the ground before, during, and after the 1991 Pinatubo eruption, and were in part responsible for the success of the evacuation response. Tonight, sponsored both by Carnegie and, as you heard, by the Embassy of the Philippines, and by the US Geological Survey, and by the Smithsonian, Doctors Renato Solidum and Christopher Newhall will tell us of their experiences during that cataclysmic time. Dr. Chris Newhall, who will speak first, is a former team member of the Volcanic Disaster Assistance Program of the USGS, who led the program's involvement at Pinatubo. He is famed not only as an expert in volcanology, especially in prediction, but as a co-developer of the Volcanic Explosivity Index, a widely used measure of the severity of volcanic eruptions. Dr. Newhall, who holds a PhD from Dartmouth College and is a past chairman of the World Organization of Volcano Observatories, has taught at the University of Washington, Nanyang Technological University, and Aquinas University. Currently, he teaches at the University of the Philippines. He first visited the Philippines in 1970 as a Peace Corps volunteer. He returned to live there in 2005 after retiring from the USGS. Dr. Solidum hails from the Philippines, where he is the director of the Philippine Institute of Volcanology and Seismology, and he traveled a long way to get here, and we are very grateful for him doing that. A widely recognized expert in the earth sciences, especially in understanding the assessments of geologic hazards, he holds a master's degree from the University of Illinois and a PhD in earth science from the Scripps Institute of Oceanography of the University of California, San Diego. In 2010, he reached the Presidential Lingkod Bayan Award, the highest recognition for public service given by the Philippine government, for his efforts in reducing disaster risk and in initiating a nationwide mapping program of tsunami-prone areas. Now, I just want to note before the talks begin that at the end of the lectures, we'll have a question-and-answer session here mediated by Dr. Diana Roman, who is a volcanologist, one of our Carnegie scientists, so stay for that. So please join me in welcoming first Dr. Chris Newhall and then Dr. Renato Solidum.
Thank you, President Scott, for the kind words, the introduction, and the invitation to join you. Ambassador Quisia, Ambassador Hubbard, and to everyone here, thank you for coming out this afternoon or this evening to help us celebrate, really, an event that took place 25 years ago, to help us remember this event, because it was indeed it had a profound effect both on the science of volcanology and on the people who lived around Pinatubo. The ambassador has better figures than I do, but I'll make very rough numbers. There were roughly 1 million people living around the foot of the volcano. It depends how far you take the radius out, including about 20,000 indigenous Aita people. There were these two very large military bases, Clark Air Base and Subic Bay Naval Station. There was at that time, I think it's fair to say, a contentious relationship between the two governments on renegotiating the bases. It was not an easy negotiation that was taking place. And the volcano itself was actually controlled at that time by the Communist New People's Army. So we had a rather diverse group of constituents to work with as we were going around. It's like culture shock every day, in and out of these different groups. The volcano had not had an eruption in 500 years, so there was no memory or familiarity with volcanic hazards. I had the privilege of leading a small team from the USGS that came over and worked with PHIVOLCS, the Philippine Institute of Volcanology and Seismology, to try to keep people safe from this evolving event. The story really began in July of 1990. There was a magnitude 7.8 earthquake that occurred about 100 kilometers northeast of Pinatubo. You can see the damage here to the Hyatt Hotel. It also had an effect on Pinatubo itself. Without going into great detail, we think what happened was that basically stress from the setup by the earthquake squeezed the crust underneath Pinatubo and squeezed some magma from great depth up, and it gradually coalesced and started to rise toward the surface. By April 2nd, 91, there were some small earthquakes starting in March, and then by April 2nd, there were small explosions that occurred along the, I'll see if I can use this. There we go. Along a fissure on the North Sea side of the volcano, and very strong steam jets on the flank of the volcano itself. You can see them here in this other view. And these deposits, by the way, in the foreground, are deposits of past eruptions that told us, as geologists, that Pinatubo had a history of very big explosive eruptions. When it reawakened, we as a team, we had these challenges. We had to do some very rapid geologic reconnaissance to try to get new radiocarbon dates as quickly as we could, to try to find out how frequently these big explosive eruptions occurred, and by implication, whether it was due or not for another one. We had to start new monitoring from scratch. There was no monitoring present at the time. VVolcs put in the first seismic network, and then the USGS team came over and added to that. We had to read the signals from the volcano. And some of that was straightforward, but some was actually quite a challenge. And because there was no familiarity with the volcanic hazard, we had a massive education job to do all at the same time, and we had quite a small team to do it. So on any given day, a scientist might be out in the morning doing geology and out in the afternoon reading seismograms or going over and giving a briefing to a governor and so on. It was a crazy, hectic time. The then director of VVolcs, the late Ray Punungbayan, did a magnificent job of managing all of this. We had, among other things, to develop simple tools that people could understand, because if we were to try to explain this in scientific terms, I think we probably would not have we would not have been able to convince people to respond as constructively as they did. All right. First question that we had to ask was, how often does it erupt? And when was the latest one? There had been a little bit of work done in the 70s and 80s for a nuclear power plant and for a geothermal drilling. The new work began as soon as we got on the ground, and the only deposits that we could find were deposits of big explosive eruptions. This is actually rather unusual for a volcano, but it turned out to be very helpful to us, because then we could say that if it does erupt, it's going to be big. These were, it's a stack of products from big explosive eruptions just outside the back gate of Clark Air Base. So, and these deposits are a thing that we call pyroclastic flows, which are a hot blast that comes down. It travels about 100 kilometers an hour. It wipes out everything in its path. Total wipeout. So to have these right outside the back gate of Clark and at similar distances around the other side of the volcano was quite worrisome. All right. So we did then try to refine it a little bit to say, all right, how far will these pyroclastic flows reach? And we could see that they reached all the way out to Clark and Angeles City, and we could see that there were lahar, or volcanic mudflow deposits, that went on from there. Both of those are lethal, So we had a major problem on our hands. This figure here, this is a SLAR image, radar image of the volcano, and taken before the eruption. And these deposits outlined, called modern Pinatubo, were products of big explosive eruptions that had occurred over the course of several tens of thousands of years previously. They had a big fan on the west side of the volcano. They came down on the southwest into Zambales, out here to the west to Zambales, and over here, coming into the province of Pampanga and Clark Air Base, you can see the runway right there. So the stakes were very high indeed. We released a hazard map, very crude hazard map based on what we could see as the extent of previous eruptions. We thought it was the worst case scenario, although in retrospect we realized we underestimated it. Fortunately, the 91 eruption turned out to match this outline just about perfectly. The monitoring, for the first 2 months, the monitoring was not very diagnostic. The volcano was clearly restless, but we could not say whether the magma was actually going to erupt. In fact, at first we couldn't even confirm that there was magma, but after a while we did. There was nothing to suggest a giant impending eruption. So at this point, all we could say was that things seemed to be ramping up. But it was not possible until June, actually, to say whether or not it really would erupt. This figure is for sulfur dioxide gas emission. The first measurement we were able to get in the middle of May was 500 tons per day, which is a kind of a, it's not a spectacular number for a volcano preparing to erupt, but it was big enough for us to say, yes, this is magmatic. It proceeded to increase tenfold up to 5,000 tons a day by the end of May. And at that point, we could say not only is it magmatic, that magma is rising closer to the surface. And then suddenly it dropped down, way down. And we didn't know quite what to make of that, but our interpretation at the time was that the magma had probably developed a carapace that was temporarily blocking the release of gas. And sure enough, by the time we got a few more measurements, by June 10th it went off scale, indicating that we were back in business again. The eruption had not gone away. The seismicity, there was a swarm of earthquakes that started about 5 kilometers to the northwest of the volcano. And then by June, it migrated right directly underneath the volcano and rose upward. And again, all of this is adding to the general pattern that magma appears to be rising. There were a number of different kinds of volcanic earthquakes that occurred. I won't bore you with the details of it, just to say that this was a very interesting set of earthquakes, some of which didn't even get recognized for what they were until after the eruption. We were going 90 miles an hour trying to just cope with the events, and there were some little subtleties that we didn't pick up on until afterwards. Just getting the network in was a huge chore. We had wonderful air support from the US Air Force and later from the Philippine Air Force and also the US Navy. And you can get a little flavor from here. The things were pretty hectic. At this point, they were trying to get a radio signal, reestablished that had been lost. So another question that we asked was, how likely are these events? And I think we've been discussing in our group discussion that President Scott was mentioning. about the value of quantifying hazards, to try to put probabilities onto events. And yet the uncertainties were very high. And so it was a question of whether we could even make reasonable guesses at the probabilities of events. But we felt we had to do that. We had to have some way to inform those who were at risk about how dangerous this actually was. And in general, non-scientists are going to have trouble with probabilities, but there are a few folks who are familiar with them and trained to use them, and that included the Philippine Civil Defense and the military officers. So we made a very simple little probability tree, and without going into details, it was the probability of having pyroclastic flows reach onto Clark Air Base within the coming few months. And the number that came out was around 3% probability. To a layman, that might seem small. It might even seem negligible. But to the military officers who recognized everything that was at stake, that 3% was very high. They just sat bolt upright, and we really got their attention from this. And the same thing with Philippine Civil Defense. I should say that in general, Philippine Civil Defense was way out in front of the US military on recognizing and responding to the hazards. We had our hardest skeptics among the US military. There were a number of other cultural and political challenges too. Skepticism was incredibly strong. Partly it's because it hadn't erupted for a long time, but there were some other factors too. There were some cultural and political factors. It didn't help that the mayor of the biggest city right there was a difficult character. And then, in addition to that, I mentioned the renegotiations. I mean, there was strong suspicion on both sides that the other side was trying to get the advantage in the renegotiation. I don't know whether the two ambassadors would agree on this, but we felt kind of squeezed in between. There was a second thing that we're geologists. We came over, we were bearded, we would go out in the field, we would dig in the dirt, we would come back, and I would come back coated with mud and dust and sweat. And you know, the military is generally pretty spit and polish. And so we didn't quite fit in. They weren't quite sure of what to make of us. Then we had the NPA, the New People's Army. They didn't trust anybody that had any connection with the embassy, and yet we relied on U.S. Air Force helicopters and vehicles from USAID, and they had embassy plates. I mean, you could have painted a target on the side of the vehicle. And in fact, when we finally did meet up and talk with the NPA high on the volcano, I was very nervous at first until the Filipinos, my colleagues on the geology side, did what Filipinos do everywhere, and that is when they meet each other, they start to find connections. They ask your family name, they ask where you're from, do you have mutual friends, and very quickly it developed that my geology colleagues, who were graduates of the University of the Philippines, had mutual friends with the NPA that we were talking with. And it just dissolved completely. There was no further problem. And in fact, they were a good audience. And then the indigenous Aitas didn't trust anybody from the lowlands, so it complicated things even further. Matt mentioned the Nevado del Ruiz disaster that killed so many people from mudfloods. After that, the volcano community made a video, a very graphic video of each of the major volcanic hazards is, how far it goes, how fast it travels, and what it does to you when it hits you. And fortunately, we had this. It was in rough cut still, but it was usable, and it was a wonderful tool for educating people about what the volcanic hazards were. We also created, kind of by the seat of our pants, an alert level scheme that ramped up from no alert all the way up to eruption in progress. The whole idea of this was to have some easy way to communicate level to the officials and to the general public. If we could go back and do it again, I might make a few modifications, but it worked pretty well. And I'll call your attention to level 2 that said probable magmatic intrusion. Level 3 said if the trend continues, it may erupt within 2 weeks, within 24 hours, and then finally eruption in progress. Well, going back to the scientific story, by early June, magma had already moved close to the surface. It was ramping up. These are different types of volcanic earthquakes on a timeline, and the SO2 gas emission had gone off scale. So invoking these alert levels, this blue one was the level 2 alert invoked back in May, and then by June 3, we invoked the level 2 alert, saying something would happen within 2 weeks. By June 7th, sorry, that was June 5th. Then by June 7th, we invoked the level 4, 24-hour window, and in fact, sure enough, magma did appear on the same day, but it wasn't the big explosive eruption that we were saying. It was a lava dome that was only visible if you were privileged to be in the helicopter flying overhead. And you can imagine the credibility gap that we had with the news media, because they were expecting this great big bang, and we could just say, well, we told you it was going to erupt in 24 hours, and it did. Yeah, sure. Well, this was the picture of the lava dome, actually, as it came out. Fortunately, we didn't have that credibility problem for too long, because things continued to ramp up, and there was still nothing that from the monitoring that we could say for sure that we were going to have this giant Plinian eruption. But from the geologic record, we were still sure that was the most likely outcome. Now, I mentioned credibility issues, and one of the things, this was the location of our volcano observatory, initial volcano observatory, in the middle of Clark Air Base. You can see the runways there. Clark is basically this triangle here. And as volcanologists, we were nervous about staying there in the event of a big eruption, because we knew that this nice flat fan that Clark was built on was built from pyroclastic flow and lahar deposits. And so we asked the Air Force if they could give us a fallback observatory location as far away, the volcano is up here, as far away from Clark from Pinatubo as we could get, and still be inside Clark. They did. They had a bunker out here that we then occupied. And you can bet that when the volcanologists moved back, so did other people. Okay, we didn't have to wait much longer. The June 12th eruption that the ambassador mentioned looked like an atomic bomb had gone off. It was a spectacular eruption. In fact, it was not a really very big eruption. In the VEI scale, it was just a 3. What was yet to come was 1,000 times bigger, but this looked big enough. This removed all doubt about whether the volcano was going to erupt. That's represented here by this spike. This is an eruption column going up to 20 kilometers. There were more during the 12th, 13th, and 14th. They got increasingly frequent. And On the 14th of June, the seismic energy release started to just shoot upward, way in excess of anything that we had ever seen before. So this was, by June 14th, already into the eruption. That was the only time that we could say, all right, now we think the monitoring is also saying, yes, this is going to be really big. So here we are. I showed you the previous one where it was just puttering along down here. This gives you the whole scale. It really shot up. The Raypunbayan had actually raised the alert level to the highest level on June 9th, and it was probably a little bit premature, but it's a good thing he did, because we discovered that a lot of people were waiting until the alert level had reached the highest level before they would move. So this gave some extra time. And here is a picture of the eruption itself. It's the best picture we have. If you were on the ground, you couldn't see anything. It was totally dark. So it's taken from space. This pink cloud here is 500 kilometers across, and Pinatubo is right there in the middle of it. Manila, 100 kilometers away, is down here, and you can see it covered most of northern and central Luzon, and the ash eventually blew off to the west. Now, I think I'm just going to make a couple more comments about scientific lessons, and then I'm going to hand this over to Dr. Solidum, who's going to carry on with the muddy aftermath. I mentioned the probable effect of the earthquake. After the eruption actually occurred, we went back and did some calculations. Ross Stein of the USGS did this. The earthquake displacement is shown here. It was 4 meters, 3 meters, or 5 meters, and that shifting of the earth caused compression over here underneath Pinatubo that we think squeezed basaltic magma upwards. And that basaltic magma is represented here. It came up here, came into the reservoir of dacite magma. It mixed with it. The result was a hybrid andesite that was buoyant enough that it rose right up through the dacite and was the first magma to be erupted. And then following that, it got the rest of the dacite going that fed the eruption. One last scientific lesson before we go to Renee. And that's the question of why was it so big? I think the answer, it has to do with gas. It's volatiles, primarily water, CO2, and sulfur gases. And there was this enormous cloud of sulfur dioxide, 17 million tons of sulfur dioxide that came out on the 15th and started moving west. By the 17th, it was over here, over Indochina. That set a world record for any sulfur emission. In fact, where's Arlen? Arlen Kruger, raise your hand in the back. There he is, back there. Arlen was responsible for the monitoring of and quantification of this huge cloud, and it was far more gas than could have ever been dissolved in the volume of magma that was erupted. And so the implication is that in addition to the volatiles that are at saturation in the magma, like dissolved, say for example with a bottle of Coke, as long as the cap is on, you don't see bubbles because the CO2 is dissolved in the Coke. Okay. But in this case, in this magma, there was so much more volatile that had accumulated. There was something in the order of 20 to 60 times more than saturation. And that's what enabled the eruption to be so explosive. There was no delay. When the volcano cork was finally removed, the eruption could tap down far down into the magma reservoir. There was no time delay, and it fed a very high, 35-kilometer high eruption column for from about 1:30 in the afternoon up until about midnight. So it was an enormous eruption, the second biggest eruption of the 20th century. And let me turn it over to Rene for him to carry on.
Okay, for those with keen eyes, you might notice that Chris used a blue background. I'm using a black and white background. Essentially, you can see the sky as blue before the paroxysmal eruption, but it turned black and white after the eruption. That's the logic. Anyway, thanks for the organizers for inviting us, and thank you for attending. Essentially, the climactic eruption of the 90-hour eruption of Pinatubo not only was very large, but it coincided with the passage of a typhoon named Yunya. So two disasters in waiting. And mentioned, it's the second largest eruption, but the largest eruption to affect the densely populated area in the 20th century. The maximum height of the eruption column was 34 kilometers, so essentially, the upper winds blew the ash further to the southwest, reaching the Indian Ocean, but the cyclonic winds pushed the ashes all around. The total bulk volume of deposits was around 8.4 to 10.4 cubic kilometers, a lot of materials. And in the picture, you will see a 6 o'clock photo of the pyroclastic flows in Clarker Bays. My role during the eruption of Pinatubo was to go closer to the volcano and sample the volcanic ash and pebbles raining over the volcano. So instead of some volcanologists getting away from the volcano, we were able to go closer. Unfortunately, by daytime of June 15, the sky was so dark already, and we got a message that we have to go back to Olongapo City, southwest of the volcano, so that we can have a good connection with the main office in Quezon City. Essentially, the cataclysmic eruption of Pinatubo turned day into night. And if you're outside of the building with no electricity, you have to stretch your hand so that you would not collide with another person. It was so dark and quite frightening if you're not a volcanologist, or perhaps more frightening if you're a volcanologist, because you would know that the volcano would blow up. So what are the geologic impacts of the volcanic eruption? Well, first, because of the tremendous volume of materials erupted by the volcano collapsed, forming a new summit caldera. There were also thick pyroclastic flows in place all over, down to 16 kilometers from the crater. There was extensive ash, sand or siltite deposits, to pebble-sized deposits, or tephra, all over Luzon, and some countries in Southeast Asia. And because of 100 degrees centigrade in 1996, there were secondary explosions triggered by groundwater reaching the base of these pyroclastic flows. And more importantly, if you think that the volcano eruption was so frightening and so damaging, wait till you see the sin and post-eruption lahars, which destroyed many villages, and the cost of total damage will be 2 times the cost of damage of the eruption. More importantly, there was significant loss of habitable and arable land. The eruption continued till end of September with minor ash, but you can see the crater there. But if you look at radar images of the volcano before and after, you would see that before there was no crater and after there was a crater. You would also notice that the slopes of the volcano were rough, and after the eruption, you would see that the slopes was kind of smoothed. Essentially, thick valleys were filled up by pyroclastic flows. Pyroclastic flows are high-speed avalanches of hot ash, pumice fragments, and gas. The total volume was close to 5.5 cubic kilometers, and the area covered by pyroclastic flow was roughly 400 square kilometers. The pyroclastic flow reached as far down and 16 kilometers away from the crater. And you can see the pyroclastic flow as those whitish areas. If you look at before and after shots of some of the river valleys southwest of the volcano, you would see that these river valleys were thickly filled with deposits. On the top, you would see Mariano River, and shown are the arrow marks of the same ridge, and the river was covered by as thick as 200 meters of deposit. In the lower photo, you would see the upper reaches of Bocao River, with thick pyroclastic flows already eroded by the year 1995. There were secondary explosions on the pyroclastic flows themselves. Those on the top left would be a giant secondary explosion at the Maraunat River. Many people thought that the crater moved down closer to the city of Angeles, thinking that a new crater was formed on the slopes. Essentially, this was produced when stream waters from rain would sip in the hot, still very hot, as high as 500 degrees centigrade pyroclastic flow materials. On this side of the slide, you would see explosion pits because of this secondary explosion. There was not much danger from these secondary explosions if you're far away from the pyroclastic flows, but it affected aviation or flights of airplanes over the Clark Air Base. With regards to the widespread asphalt, immediately after the eruption on June 16, and if you look around, you might have thought that there was snow all over Pinatubo. All the whitish colors there are ashes from the volcanic eruption. And a total volume of 3.7 to 5.3 cubic kilometers of ash was deposited and scattered all over. Luzon Island, where Pinatubo is, was covered by ash, and around 4 million square meters of the South Tennessee area was also covered with ash. And fine ash fell as far away as the Indian Ocean. Fine ash circled the globe several times, and these caused several aircraft further west of Pinatubo to be affected by the ash. Although we saved a lot of lives because of the accurate prediction, many deaths attributed directly to the eruption were caused by the asphalt and not by the pyroclastic flow. There were thick pepper deposits on the roofs and vegetation. On the right, you would see coconut trees folded like a big umbrella. And because of the passage of Typhoon Yunya and causing heavy rain over the area, thick ash was made heavier by the rainwater that got soaked in. And because of this, many roofs collapsed and many people died because of this, roughly 300. Shown on the left would be aircraft hangar in Clark Air Base. And on the right is a hospital in San Marcelino Zambales that got collapsed during the paroxysmal eruption phase. Aside from that, the climactic eruption of Pinatubo released 20 million tons of sulfur dioxide into the stratosphere. And the sulfur dioxide gas was converted into sulfur aerosols that essentially blocked the rays of the sun to reach the lower part of the atmosphere, causing the temporary cooling of the Earth's temperature by half a degree from 1992 to 1993. Essentially, this is a reverse greenhouse effect. In fact, some scientists years ago proposed that you can combat global warming by firing sulfur dioxide-laden rockets into the stratosphere. However, the sulfur dioxide aerosol also facilitated chemical reactions that freed chemical compounds to destroy the ozone layer. So there was unprecedented increase in size of the Antarctic ozone hole in 1992. Not a good idea to fire sulfur dioxide into the stratosphere. Overall, around $230 million worth of property, infrastructure, agricultural crops, and forest land were destroyed. More than 1 million people were affected. 20,000 itas were displaced, and 300 people died because of roof collapses. However, because of the successful monitoring and warning, the timely forecast of Pinatubo's climactic eruption by scientists both from PHIVOLCS and USGS, enabled people living near the slopes of the volcano to evacuate to safer distances, including volcanologists, saving at least 5,000 lives and at least $250 million in property. More importantly, commercial aircraft were warned about the hazard of the ash cloud from the June 15 eruption of Pinatubo, and most of the aircrafts avoided it. However, a number of jets flying far to the west of Pinatubo encountered the ash and sustained considerable damage. Although the eruption died down in September, our problem has just started. Because of the enormous amount of volcanic materials on the slopes of the volcano, brought down by pyroclastic flows and the asphalt deposits, volcanic mudflows or lahars became a long-term threat. Lahar is an Indonesian term for volcanic mudflows, and these would be typically triggered by rainfall either through monsoons or typhoons, sometimes lake breakout, or in other countries, melting of the ice caps on volcano summit. It can be a longer-term threat after a large explosive eruption, and in Pinatubo, created damage more than twice the damage of the volcanic eruption. Essentially, lahars are a mixture of volcanic sediments with water, so sometimes lahars with more than 80% sediment would look like concrete being poured down on the river. Because of the tremendous amount of pyroclastic material shown in the map as pink, and shown on the right as this very erodible materials, we thought that the lahars would continue to threaten the slopes of Pinatubo at least for 10 years or more. And there were 6 major channels shown there on the map as green to yellow colored areas that would drain the Pinatubo pyroclastic flow for a long time. Estimated annual sediment volumes by year are shown. Around 1.2 to 2.5 billion cubic meters of erodible materials are expected to move down the slopes for 10 years if rainfall is distributed equally all over the years. Of course, from time to time, there will be intense rainfall, and so this was not exactly followed, but overall, the significant lahar events moved down the slopes of the volcano until 1996 and slowed down years after that. You would see that the impacts of lahars are quite significant. There are burial of river channels and adjacent low-lying areas. Shown on the top would be 2 pictures before and after, 1901 and 92, of a river channel just at the northern boundary of Gardner Base, and you would see the rooftop of the building directly covered with lahars. Schools were buried, and Filipinos maintained their high spirit even after a major disaster. And you would see school kids smiling after a major lahar event, perhaps because they don't have classes, or perhaps they're just aware that their photos are being taken. But essentially, you would see the tremendous amount of deposits covered the low-lying areas and displaced hundreds of thousands of people because of lahar events. Bridges were destroyed, like this bridge in western Pinatubo, or roads and bridges were buried. So sometimes isolation can happen and mobility will be affected during major eruptions. There were also development of lakes because rivers or streams were blocked or dammed by lahar deposits. Shown on the left is the Marela lahar deposit that would drain towards the right side. But a lake was formed out of a river called Mapanueco River, and this became a lake. Water rose and essentially flooded communities further upstream of the river, and this is actually a mining community, and many people lost their houses because the water just rose and rose. More importantly, the significant amount of sediments buried not only agricultural lands but also settlement. This is the town of Bacolor in Pampanga, southeast of the volcano, and you will see that prior to the Lahar, you would see a vibrant community, and after the Lahar, you would see vegetation wiped out and many houses buried. This is a scene all over Luzon, areas covered by lahars. So the government has to do something to prevent further loss of houses and even loss of lives. So we monitored the lahar events using seismographs. In addition, the Philippine National Police manned several rivers draining Pinatubo, and they had watch points to monitor the passage of lahar so that they can warn the people if there is a lahar coming from the mountain. But the most important mitigation measure for lahar was kind of expensive. We have to make sure that rivers would have enough capacity to still receive a lot of volcanic sediments after major lahar events, and we tried dredging. But we cannot outrun or outpace nature. So government has decided to construct very wide dikes as high as 4 meters, and this would entail sacrificing some communities while protecting others. It has proven effective, but in the long term, the channel dikes will be filled up by sediments, so the threat not only of lahar but floods would still linger on. For those with lakes, so that the flood would be lessened, we established canals to drain the dammed lake in the southwest side of Pinatubo. Well, we thought that the lahar threat would be quite minimal, since we're lucky enough that the Pinatubo area has not been affected by heavy rainfall after the eruption. However, because of the big crater on top of the volcano, we have to worry that the lake water will be filled up to the brink, and later on this water would break out and move towards the northern side of the volcano. Before I continue, let me mention that after the 91 eruption of Pinatubo, the lake was filled, the crater was filled with water, and by July of 1992, a lava dome grew at the center of the volcano. Fortunately, this lava dome did not result to a more explosive eruption, and if I did not mention that there's a lava dome in the center, many people would not know that there was an eruption in 1992. However, by the year 2000, the water filled up the lake and reached the lowermost part of the crater rim, or just barely reached it. So we have a problem, because if there is a breakout, then lahars would drain the Pinatubo crater along the Marunot Nuts and run all the way through towards the west of the volcano and may inundate Motolan town of Zambales, which would have roughly 30,000 people in population. The mitigation measure decided by the government was to intentionally breach the Marunot nuts, because the nuts is essentially made up of erodible 1991 pumice material deposits and 3 1991 breccia units on top of a hard dacite rock. So the idea was to excavate a canal 4 meters wide and 4 meters deep, and essentially evacuate the people during a non-rainy day so that we can have a controlled breaching. However, this is the size of the canal that was established, not to the specification that we advised the engineers to do. So essentially, the lake water drained and reached a certain equilibrium level, but there was no breaching. In the short term, it lessened the amount of water that will be filling up the lake, so perhaps the amount of lahars that would be developed if the crater would break out will not be as much. But that would really pose a big danger if there will be a lot of rainfall over the area. In 2002, a typhoon called Gloria passed over the northeast side of the Philippines in the Philippine Sea, and this essentially enhanced the southwest monsoon from the Indian Ocean, and from July 1 to July 9, 740 millimeters of rain was estimated to fell on the crater. Essentially, we converted this to a 1 meter rise in the lake level, and we thought that there's a chance that the crater lake would break up. So I convinced Dr. Punong Bayan to send 2 of my geologists to the area on July 10, 2002. And when they reached the area, they saw the Lahar almost overtopping the bridge connecting a big part of Zambales to Butuan town. So what happened was, the hydraulic gradient enabled the erodible materials to be eroded and carried with it tremendous amount of lahars that were brought down to the South China Sea. It indeed overtopped the Bukaw Bridge over here, but it did not overtop the protective dikes that were protecting Botolan, and fortunately, because of this, there was no casualty. Upon investigation of the main crater, we saw this high water mark on the crater walls beside the Marunat rocks, and the water dropped by about 21 meters. So we think that the drain canal was very important, because if we did not do the drain canal, natural overtopping of the lake water would have released 80 million cubic meters of water, and together with the erosion and bulking up of the flood water with sediment, a breakout lahar with a volume of more than 185 million cubic meters would have been delivered with a very high discharge. Because of the drain canal, 15 million cubic meters of water was prevented, and instead of having more than 185 million cubic meters of lahar draining down the slopes of the volcano, we were able to lessen it, and it did not overtop the dike, and that is why people did not die. Lahar will be a continuing threat over the Pinatubo area. Major rivers are filled up with volcanic sediments. For example, this is the Santo Tomas Marela River, and you would see the dike there, and the outside of the dike much lower than the riverbed. Sedimentation will continue with normal stream flow or lahar events, and definitely there are stretches where riverbed is near or the same level as the confining dikes. Because of this, the potential for breakout of floods or lahars from these dikes and remobilization of these sediments can happen, and this would require continuing vigilance and monitoring of these dikes and lahar sediments. So although the eruption has been finished 25 years ago, the lahar threat is still continuing. The danger is far from over. So what can we learn out of the Pinatubo experience? One of the lessons is that it is important that scientists, disaster managers, local government officials, national agencies, and armed forces, both the police and the military, work together for effective emergency management. Scientists can do a good warning, but if people are not evacuated fast enough, people will die. The Pinatubo experience also highlighted the importance of scientific information from modern multi-parameter instrumental monitoring, combined with field and remote sensing surveys for appropriate prediction of eruptions and areas that will be impacted and need to be evacuated. It is also important to use various methodologies to communicate the hazards to people, especially those who have not experienced any eruption. So the use of documentaries like the craft video for communicating hazards, community-based information campaigns like going all around, and simple volcano alert level schemes for warning were indeed very useful in communicating the hazard and letting the people understand the hazards and the risks that they face. However, we should not stop monitoring the volcano. You are all invited to go to the volcano and visit the crater, but during rainy seasons, you must avoid the lahar channels draining the slopes of the volcano, because processes as lahars, which compose lingering threat many years after the eruption, still persist. So ladies and gentlemen, both Chris and I dedicate this presentation to the people of Pinatubo, who despite the dangers and negative experiences they have, still persist to live within the volcano. And we also look forward to the application of all the lessons, scientific lessons, partnerships, friendships that we have developed, making sure that we apply the lessons in other volcanoes, not only in the Philippines, but in other parts of the world, so that we can have communities living safely with volcanoes. Thank you very much.
Thank you so much, Dr. Newhall, Dr. Solidum, for that fascinating retrospective of a truly remarkable geological event. And as a volcanologist myself, I can definitely confirm that when the guys at the observatory start backing away, you know something bad is coming. We have about 10 minutes now for questions from the audience. There are microphones in both of the aisles. So if you have a question, please just line up behind one of the microphones. We'll go for about 10 minutes or until we finish with the questions. Go ahead, please.
Jim Lowen, I'm a sociologist, so naturally I'm interested in the indigenous people that all had to leave. I wonder if you could tell us a little bit about their culture, about how they supported themselves, and what in the world they are doing now.
Essentially, before the eruption, they were just essentially living through farming and hunting. And so the mountain was their place. The mountain and Pinatubo was their god. So obviously during the eruption they got displaced and they got resettled in areas that were in a safer place away from the volcano. So they're trying to rebuild their lives in a different area, but of course it's not the same as before. And essentially it has been a culture shock for many of them to be displaced from the volcano.
So they're agriculture. They found some. I mean, the Philippines don't have a lot of abandoned land or available land. Are they in cities now? Are they?
Well, they were resettled in places, but unlike before, where they can roam around, they're in a more or less confined space. However, I think with time, if vegetation would recover, actually we have a law that says that Pinatubo is an ancestral land, and maybe perhaps if everything will be recovered, they can go back. But in the meantime, they stay in the resettlement.
Thank you very much. My name is Alexander Kravitz. I'm originally from El Salvador, so obviously I have, even though I'm not a scientist, I have an interest in the topic. I'm wondering if, as a result of what happened, let's say a culture of prevention grew in the Philippines, in terms of curriculums of the students. I mean, just kind of making people, more aware of the dangers and sort of, I know it's very difficult to plan for these kind of catastrophes, but to the extent that there's advanced preparation, you talk about the military, the scientists, disaster managers working together to the extent that you can plan ahead and prepare. So I wonder if you could tell us a little bit about that.
Well, because of what happened in Pinatubo and the 1990 earthquake, our advocacy now is to prepare scenarios that can be shared with the public. So we've prepared hazard maps and volcano scenarios for different volcanoes. We have prepared earthquake hazard and risk scenarios for Metro Manila. And so, giving them full accounts of what can happen in terms of death and casualty. So, what we're trying to do now is giving them a way for them to have a picture in their mind of what can happen and what they're supposed to do so that they'll be able to live and survive the impending disaster. So the Philippines is blessed with many hazards, as you know. Name all the hazards we have it except those related to snow. And so we need to make sure that people know which hazard will affect their respective areas. and how we can prepare for it. It's a tough job. That's why it's important for us to collaborate with as many people as possible. The role of non-government organizations or civil society organizations is very big in the Philippines, and we have a lot of those. So the whole of society needs to be involved. So education is a big part of our advocacy.
Thank you very much.
How do you measure and quantify sulfur dioxide volume?
Yeah, it's a UV sensor. It was actually a sensor developed for monitoring ozone in the atmosphere, but the algorithm was adapted to quantify SO2 as well. And I'll refer you perhaps later to Dr. Arlen Kruger in the back, who is one of the people who developed that algorithm. But it operated basically, there was one shot per day, I believe, at 10 a.m. in the morning, and so we got one measurement per day.
You place the sensor on a plane, and the plane would have to pass through the steaming column of the volcanoes. It's quite dangerous.
Actually, there were two methods. One was applied from the plane, as Renee is saying. The other was from the satellite. For monitoring the buildup from 500 to 5,000 tons a day, that was done from the plane. To measure the 17 megatons, we needed the satellite.
Thank you for two fascinating presentations. I'm Liz Cottrell. I'm with Smithsonian's Global Volcanism Program, and my question is for you, Chris. I'm familiar today with how VDAP is deployed during a volcanic crisis, but you kind of started your talk with, you already had boots on the ground there at the beginning of your talk, and I'm curious as to how VDAP in its early days there, how was it decided, what was the chain of events that decided to deploy you and your team, both geologically, how did that come about that it was decided that we needed a deployment, and then also in the early days of VDAP politically, how that worked?
Oh my, that's a long story. I don't think we'll keep the audience for the whole story, but the short answer is that this was shortly after the Kuwait War, and OFDA, USA OFDA was heavily involved in the recovery effort in Kuwait. They were not, frankly, much interested in sending the USGS over to help in the Philippines. And furthermore, I'd say it was really much more of a personal friendship between Ray Kunenbein and myself. I got a call from Ray shortly after the small explosions in the beginning of April, and Ray did not ask for help. I sort of read between the lines, and I asked him if he would like some help from us. He said yes. Then there was a negotiation with USAID. The bottom line was that we went over as scientific colleagues. Technically, it was not a VDAP response at the very beginning. It became one later on, and we were actually winging it in some important ways, including not having any money to work with. I was writing IOUs out by the day. It all worked out in the end.
I'm curious, 25 years later, how the predictive modeling has evolved, and what are you looking at now, or what do people look at as the next Pinatubo, and what kind of time frame? Do you have any greater forecasting capability now than then as a result of the work?
Well, prior to the Pinatubo eruption, we had exactly 0 prior cases of monitored Plinian eruptions, eruptions of that scale. Now we have 1. Actually, it's a little better than that. We have learned from a variety of volcanoes over the years. So I think the art and the science of forecasting eruptions has improved considerably. We have a lot of new technology that we didn't have back then. We have GPS. We have radar interferometry from space. There are a variety of new instruments. So I think the combination of lessons learned on the ground from these volcanoes plus the new technologies puts us in a much better position now to make good forecasts. Now, as to the next Pinatubo, I don't think I'm going to go there.
We have a volcano similar to Mount Pinatubo in the Philippines called Mount Parker. It last erupted in 1641. The style of the eruption is the same. I've studied the chemistry. And the palisades are all over. Second more important clue for me is that the Americans built the Clark Air Base. And they helped us build the runway of the airport on the slopes of the Mount Parker.
I know there are several people lined up with the microphones, but I've just been alerted that we have time for 2 more questions in the formal program, so we'll take the 2 folks in front of the lines there, and maybe there will be some time for informal discussion afterwards.
Thank you. I'm in the warning business, and I'm also an educator. I found the comparison of the 2 volcanoes very interesting. You talked about Del Ruiz and Pinatubo, and they had very different outcomes. I assume I'm not fully aware of, so I'll defer to your expertise. I'm sure that the local cultures were very different. And I was wondering if you could comment on how you think the different cultures may have affected different outcomes in both cases, and whether or not a key ingredient, which I believe may have been involved, and that is hubris.
I'm not sure hubris was much involved. The one thing that made a very, very big difference was having the video of the main volcanic hazards, because prior to that, all we had were our words. And we would give briefings and we would make maps. We would lay maps out on the table. But I think our experience has been that many people really don't gain very much by looking at a map. It's a little bit too abstract. And the words, you know, the expression, a picture is worth 1,000 words. Well, boy, a video is worth 10,000 words. It really, really helped. They didn't have it in the case of Nevado del Ruiz, and I think that's why people didn't move, because they didn't understand what was coming at them. In Pinatubo, they did understand.
So without that, it would have had a different outcome, you
I
think?
think so.
Okay, thank you.
Certainly at the time you were primarily interested in protecting lives. Thank you very much. But in retrospect, what areas of volcanology did you learn the most about?
I'll take a crack at that. To me, the biggest scientific revelation has to do with the volcanic gases and the amount of gas that can accumulate in the magma. It's really changed the way we view gases in magmas. We know now that it can accumulate far in excess of saturation. This is actually something that the late Jim Lure from the Smithsonian had inferred correctly from El Chichon volcano in 1982. And I think, you know, those of us who had read the paper sort of understood it, but it wasn't, I don't think it was a part of our everyday thinking. Boy, Pinatubo drove it home that there are some magmas, particularly in volcanoes that have been plugged up for hundreds of years, that have accumulated very large amounts of volatiles, and those are sitting happily down there as little separate volatile bubbles in the magma, just waiting for the cork to be popped, and then it can really drive a huge eruption. It looks to me as though that's a necessary condition to have Plinian eruptions, these largest explosive eruptions. I suppose there were many other scientific lessons as well, but that's the one that I think stands out for me.
Okay, thank you. And that concludes tonight's formal program. Thank you very much for coming and for your questions. Please join me one last time in thanking tonight's speakers.